Hello, welcome in. We are covering the subject thermodynamics for civil services mains, IFS and various gate exam, and we are covering the chapter first law of thermodynamics, and in this chapter the next topic is specific heat, and the definition of specific heat is specific heat of a solid or liquid is usually defined as heat required to raise unit mass through 1 degree temperature rise. So if we take mass is equal to 1 and take temperature rise of this mass equal to 1 degree, then what is the heat required in your specific heat? So for small quantity this can be written like this: dq is equal to mc dt. So m is mass, c is specific heat due to temperature rise, and dq is the heat. So there can be many specific heats. Okay, so there can be many specific heats. So there are infinite number of specific heat depending on the process we choose. But here we will consider only two types of specific heat. One is at constant volume and other is at constant pressure. So here if we take constant volume process, then dq is equal to cv dt, and if we take first law of thermodynamics for constant volume process, the work done will be 0 because there is no change in volume. So du, according to first law of thermodynamics, du will be equal to dq is equal to cv dt. So now if we integrate it, it will be u cv t plus k, where k is your constant. And if we take t is equal to 0, then u will be 0. Okay. We will assume that. Then k will be 0, and then so if we take mass m, then internal energy will be your mcv t, and change in internal energy is your mcv t to minus t. Okay, so these are the change in internal energy, and these are the Cp and Cv are the specific heat. For constant volume it is Cv, and for constant pressure it is Cv. So now we will draw the relationship between these two specific heats, Cp and Cv, assuming a constant pressure process and applying first law of thermodynamics. Then Q will be equal to U2 minus U1 plus W, and U2 minus U1 is equal to mCv T2 minus T1. So that is your change in internal energy for any process. Okay, because we have tried this mCv T2 minus T1, and for putting the value here we will like this. So now if we take W is equal to P V2 minus V1, because it is constant pressure process, then W in the constant pressure process is P V2 minus V1, and P1 V1 is equal to M using this ideal gas, characteristic gas situation. P1 V1 is equal to MRT1, and P2 V2 is equal to MRT2. So W will be your MRT2 minus T1. So now we put the value of W here and U here. Then Q is M CV plus R within bracket into T2 minus T1. Okay, but for a constant, because we are considering constant pressure process, but for a constant pressure process, Q is your MCP T2 minus T1. We put it here, then MCP T2 minus T1 is equal to MCV plus R within bracket into T2 minus T1, and CP is equal to CV plus R, and CP minus CV will be a R, or that is your difference. So CP minus CV is a difference. And now we'll find out the ratio also. So if we divide this equation by CV, then it will be CP by CV minus CV by CV is equal to R by CV. So this is your 1, and this is your gamma. This is R by CV, and CV is your R by 1. If we divide it by CP both sides, then it will be CP by CP minus CV by CP is equal to R by CP. So Cp will be your R gamma by 1, and where gamma is your specific heat ratio. Cp by Cv is your gamma. Okay. So as we have seen that Cp is equal to Cv plus R, So Cp is always more than Cv, because Cv is less than because R is added to get Cp, so it means gamma is always greater than 1. Okay. For monatomic gas, gamma is 1.66, and for diatomic gas like CO, H2, N2, O2, gamma is 1.6, and for triatomic it is 1.3, and for ethane it is 1.2, and for isobutane 1.11. So these are the values of gamma.